Hi friends, we are working on finding the distance from one node to other node in a graph. We had seen how Dijikra's algorithm and Bellman-Ford algorithm can work, and also seen the drawbacks of Dijikra's algorithm or shortfalls of Bellman-Ford algorithm. Yeah, that's all are there when we have a negative weights, but in the given graph, we are using an example where there is no such negative weight, and hence there won't be a problem even with the loop or without loop, whatever way you consider. Yeah. And another issue is the discharge and Bellman-Ford algorithms were defined for directed graphs, but here we have an undirected graph, so not an issue. So an undirected graph may be converted into a directed graph by using two arrows between each pair of nodes, and that's it. Anyway, doesn't make much difference because the adjacency matrix for this is always symmetric, and hence just following the adjacency matrix will solve the problem. Whether you treat it as a directed or undirected doesn't make much difference. So because there are no negative weights, and the loops will not make any problem because of only positive weights. Therefore, the discharge method or Bellman-Ford method are going to give the same result. So here we have that. Shortly I will just see. So we start from A. We are looking for the shortest path from A to J. So from A we started. So it's 6 and 3 for B and F respectively, and then we find that going to F is better idea because it needs only 3. So let's go to F, and from F we go to G and H. So it is 3 plus 1 4 to G, and 3 plus 7 10 to H. So once we come there, we realize that G is having smaller distance from the source. Therefore we continue from G. So we go to I. From G to I it is 3. So 4 plus 3, I makes 7. Done. Then we realize that from the remaining 6 is 10 7. 6 is the smallest, so we get from B. From B we get C and D values 9 and 8 respectively, and then they realize that extending I is beneficial. So we started extending from I. So it could go to E, it could go to J. Going to J, it makes 3 plus 1 plus 3 plus 3, that is 10. And going to E, 3 plus 1, 4 plus 3. So we get a 12 for E. So we had a problem here. We could have got 12 in the beginning itself, the first. So when you work from I, we could have got it. Okay, so that makes 12 here. So that's going to solve this problem. So we have 12 here, so nothing to worry. So finally we get a 10 here, and if you look at all other things, we realize that the remaining thing is 12 and 10. So that is still halfway. So we have reached H in 10 units, but on the other way we have already reached J in 10 units. That means reach the goal in 10 units. So halfway 10 units has no meaning, and same way somewhere on the way more than the final answer also doesn't make any sense. Therefore, so we are left with one answer. So that says that you go from A to F, F to G, G to I to J. Yeah, that's one. Now if you look at it, we are going to work with n square workspace. and so hopefully the work is out of L square. Yeah, the other side we have an A star, which is an intelligent algorithm. So it's an intelligent algorithm, and what it does is it has got two values, f and sorry, g and h. So g star talks about this actual distances or the actual weights between the any two nodes, and where h is the heuristically measured distance to the destination. So some rough idea we have that destination is so much away, that's heuristically measured. So here along with g value, so these all are g values and these are h values. So it says that A is approximately 10 units away from the destination, F is 6 units away from destination, H is 3 units away from destination, B is 8 units away from destination, and so on. So that way it the data is available to us, and we work with this data as a path, then G of the path and H of that, and G plus H. So we begin with A. A is a initial node, so the distance from A to itself is 0, and the approximated distance to the destination, it is found to be 10, so that's going to be 10. Then you can go to A to B and A to F. So if it is A to B, the distance from A to B is 6, and at B we know that B is approximately 8 units away from the destination, therefore that makes 14. On the other side, F is 3 units away from A, and it is said approximately that F is 6 units away from the destination, so that makes 9. So among this, 9 happens to be the smallest, therefore it is advisable to extend from F. From F we have two more possibilities, G and H. So AF, G, AF, H. So if you look at AF, G, so A to F is 3, F to G is 1, so that makes 4. The G value of AFG is 4, whereas the heuristic value of G node is 5, so that makes 9. Same way, AFH, it is 3 plus 7 is 10, is the G value, and heuristic value of H is 3, so that makes 13. So whom should we take next? Yeah, next value is AFG. So from G, if you want to extend, it can go to I. So A, F, G, I. A, F, G, I is 3 plus 1 plus 3, that is 7. And the value of heuristic at I is 1, so that makes 8. So among all, 8 happens to be the smallest, so let us extend from AFGI. So AFGI, it can go to E or it can go to J. AFGI can go to G, can go to E or AFGI can go to J. So if it goes to E, then 3 plus 1 plus 3, 7 plus 5 is 12. And heuristic value of E is 3. So that says us that it's approximately 15 units this path will take. Whereas AFGIJ, AF3, FG1, GI3, IJ3. So 3 plus 1 plus 3 plus 3, that's 10. And we have reached the destination, therefore nothing to extend. So we have reached destination. Now what should we do next? So should we try other paths? Of course not. Why? Because it says AFGIJ has a total path length of 10, whereas the first one, we are still at A, so that's a lot of way to move, and that's saying 10, so maybe that's has already given us correct answer. Okay, going to B, it says that it has to take 14 units, but we have completed in 10 units, so nothing to continue. Then going to H, it says 13 units. Going to E, it says 15 units, so which are greater than 10, therefore that's the best answer. So our best answer is A to F, F to G, G to I to J. So in doing that, how many steps we took? 1, 2, 3, 4, 5, 6, 7, 8 steps. Whereas here it was order of n square, whereas here that's going to be something order of n. So we are working more intelligently, and what all this talk about, how these heuristic values are measured, and how these actual values are measured, is we can take up in further examples. So that's just an idea how A star algorithm works. So it's an intelligent way of working, wherein we get two things. So what exactly we are trying to do is, so from one end we are trying to start from the source, and on the other end we are trying to end into the target. So this thing is unknown. So this is a node A, this is node A, node B, node B, node C, node C, node D, node T, and so on. So this an unknown part is there. So it says that if you are at A, then these all are talking about our H values. And if you are at starting from source, so we are talking about G values. So these values are known. If you look from the source, these values are known if you look from the destination point, and in between the paths are unknown. So we just keep moving this boundary downwards and this boundary upwards till they meet, and that's the logic of A star algorithm. So many more details to come, so keep watching. Thank you.